Hi, I'm Will Tubbett. I'm a PhD student at the University of Cambridge, and I'm going to be talking about some recent work combining pseudo-point and state space approximations for Gaussian processes. This is joint work with Arno Solin and Rich Turner, my supervisor. So we've been doing this in the context of spatiotemporal GPs, and we're interested in these because there are lots of spatiotemporal problems, for example in climate science or epidemiology, and we think that GPs are good candidate models for a lot of these things, and we'd like to be able to try them out. Of course, we run into the usual scaling issues with GPs quite quickly, because these spatiotemporal datasets can be quite large. So the kind of driving thought behind this work is, well, pseudo-point approximations, which are one very popular class of approximations, really good at space, really bad for time series problems. They really break down in time series contexts. State space approximations, on the other hand, are fantastic at time. They really do struggle with large spatial dimensions, though. And so it'd be nice if you could combine the two and get the best of both worlds, and it turns out you can in some situations. And when you do so, you get much more scalable solutions, and you can get some really clean results as well, like closed form optimal approximate posteriors, and kind of getting analogues of the standard pseudo-point methods, like Titius's variational formulation, FITC, DTC, etc., etc. So diving right into it, first ingredient, pseudo-point approximations. Basic idea is you want to construct a variational approximation to the exact posterior of your Gaussian process, given a load of data. You do so by picking a collection of pseudo-points that induce a Gaussian process, and you kind of wiggle around the pseudo-points such that this approximate posterior is close to the exact posterior. Second ingredient, state space approximations. The idea here is you take your original process F, you add a couple of extra latent dimensions, get a kind of multi-output GP if you like, and we'll call it F bar. And you do this in such a way that F bar has a Markov property through time. And the benefit of doing this is that all of your operations that you would want to do, such as log marginal likelihood computation, posterior sampling, posterior marginal computation, can be done much more efficiently and in linear time using kind of standard filtering and smoothing algorithms. The third property is separable kernels. So the basic idea is, if you have a kernel of this form, where, for example, you have your kernel over space and time comprises the product of a kernel over space and a kernel over time, then you have this conditional independence property. Now, this is not our work, this is something Antonio Hagen noticed in 1998. And it's most easily seen graphically, so the basic idea is, if you have a Gaussian process through space R and time Tor, the process at the blue square is independent of the process at the empty red square, given the process at the black circle. So if you take those three things, do some kind of careful selection of pseudo-points, you can get an efficient approximate inference scheme. The optimal approximate posterior turns out to be Markov, which is really nice. So the Markov property of the state space approximation has been preserved. You can do approximate inference by running exact inference in an approximate model, which means you can get code reuse, and it's kind of fairly easy to implement. And of course, we get better scalability. So the take-home message is, take state space approximation, construct a pseudo-point approximation to it. Given a couple of constraints, you get efficient and accurate approximate inference.